It is probably true to say that the concept of yield stress is very well known to rheologists, and that most would be able to provide an acceptable definition. In this connection, the 1975 British Standards Glossary version would not be too far from that of most rheologists. It is that stress below which the substance is an elastic solid and above it a liquid. It is also generally accepted that many everyday products seem to possess a yield stress, including clays, toothpastes, drilling muds, foams, plastic explosives, ketchups, all sorts of creams, and many other diverse materials. In their book, Rheology, An Historical Perspective, Tanner and Walters point out that the concept of yield stress was apparently first described in detail by the Russian scientist Theodor Shvedov in the late 1880s. Interestingly, Shvedov introduced a variant of the well-known Maxwell equation of linear viscoelasticity. In this equation, sigma y is the shear yield stress. Moving to the 20th century, the name of Eugene Bingham figures prominently in the unfolding yield stress story. Interestingly, it was Bingham together with two friends, Reiner and Scott Blair, who were responsible for the introduction of the term rheology, and for the setting up of the first rheology meeting in 1929. Bingham was also to give his name to what has become the most famous equation in the yield stress field, called appropriately the Bingham equation, and originally introduced as early as 1916. Here sigma y is again the yield stress and eta p the constant plastic viscosity. Barnes has described these and related developments in a series of papers. Notable amongst the developments has been the search for generalizations of the Bingham equation, and the names of Casson and of Herschel and Bulkley have been assigned to the most popular. Alongside these attempts to describe yield stress behaviour theoretically must be a discussion of the experimental evidence for the phenomenon. In this connection, an obvious example of a common material that seems to possess plastic properties is toothpaste, of course. For example, we expect a good toothpaste to be solid-like at rest, so that it will not flow under its own weight, in the tube or on the brush. It can easily be made to flow by applying a sufficiently high stress, and, in normal circumstances, it would have the necessary mobility involved in the brushing action. Margarine is another example of a material that appears to possess plastic properties. Indeed, a good margarine must have convenient plastic properties over a range of temperatures, so that it maintains its block shape for long periods, and yet is spreadable. Indeed, the old television advertisement made it quite clear that we should be able to spread a good margarine straight from the refrigerator. Or to quote another TV advertisement, it has to be firm on the knife but soft on the bread, i.e. solid-like at rest, on the knife, on the table, in the refrigerator, but liquid-like under the severe conditions involved in the spreading action. Our colleague Howard Barnes has provided us with a good example of the practical utility of the yield stress concept. This involves the industrially important process of mixing. The material in this particular example is placed in a cylindrical vessel which contains a shaft and two impellers as shown. The speed of the shaft is increased in stages from a minimum of 12 RPM. Now before the test, the material around the lower impeller is coloured with a green dye, and the material around the upper impeller with a reddish-brown dye. This provides one simple way of estimating the degree of mixing as the shaft speed is increased. The particular material in the present experiments is a 0.3% solution of carbopol in water, which is thought to possess a yield stress. Clearly, in the mixer, the stress decreases the further we move from the impellers. When the stress in the carbopol solution drops below the yield stress, any motion appears to cease, and we essentially observe a solid-like response. Loosely, we can view the coloured regions as experiencing mixing with essentially no movement, and therefore no mixing, outside this region. Not surprisingly, the coloured regions are seen to increase in size as the rotational speed of the impellers is increased. The mixed region is called a cavern. Those who use this technique believe that the diameter of the cavern can be calculated from a knowledge of the power input, the mixer geometry, and the yield stress. Amongst the techniques that are commonly used to measure the yield stress are the slump test and the vane technique. To explain the former, we shall call on our collaborator David Boger to describe in his own words work carried out at the University of Melbourne in Australia.
The video sequence demonstrates a slump measurement utilizing a cylindrical slump rheometer, the 50-cent rheometer. The slump test was initially developed to determine the flow properties needed to measure the consistency of fresh concrete. Here a large inverted cone placed on a solid surface was used with the concrete loaded into the small end of the cone. The cone was then raised and the amount of slump, that is, the decrease in the height of the cement relative to the original cone height, was measured as an indication of the flow characteristics of the concrete. The slump test, as it turns out, offers a quick and easy way of measuring the yield stress of suspensions without the need for sophisticated electronic equipment. The slump itself can be related directly to the yield stress through a model that was originally devised for the conical slump test by Murata in 1984 and later corrected by Christensen in 1991. The conical case was deemed to be more complicated than necessary, and the theory was modified for yielding using a hollow cylinder. The video sequence illustrates cylindrical slump measurements of a mineral suspension, a bauxite residue waste generated in the alumina industry. The conical slump test and analysis was developed at the University of Melbourne in conjunction with Alcoa of Australia. The first sequence illustrates the slump using a beer can, and clearly illustrates that the aspect ratio of the cylinder is too large. The next sequence illustrates carrying out the rheological measurement itself, where the cylinder is slowly lifted, allowing the material to slump. In the next sequence, the slump height is measured with a ruler. This height is directly related to the shear yield stress. There have been a number of publications since the original cylindrical slump publication where refinements have been made to the theory. But for practical purposes, the simple equation for the cylinder given by tau y prime equal 1/2 plus 1/2 the square root of s prime is sufficient for determination of the yield stress in industrial applications. Tau y prime is a dimensionless yield stress given by tau y divided by rho gh, and S prime is a dimensionless slump height given by the actual slump measurement Z divided by the height of the slump cylinder H.
In the foregoing, we have taken it for granted that the yield stress concept is soundly based, in both theory and experiment. However, in 1985, Barnes and Walters caused quite a stir with the publication of a paper entitled The Yield Stress Myth. The ideas were first put forward in 1984 at the 9th International Congress on Rheology, held at Acapulco, Mexico, and later published in Rheologica Acta. Barnes and Walters provided experimental evidence that the derived yield stress for a PVA latex adhesive depended on the rheometrical device employed, and more particularly on the low shear rate range attainable. We show two shear stress shear rate curves, the first being obtained from an early laboratory viscometer, and the second, lower curve, being obtained from a more modern control stress instrument. As we see, this was able to reach much lower shear rates. From the data in the top picture, a yield stress of 9.5 pascals was predicted, while no yield stress was needed to interpret the data in the bottom picture. Here, Newtonian behaviour is in evidence at the lowest shear rates. On the basis of this and other experimental data, Barnes and Walters postulated that if a material flows at high stresses, it will also flow, no matter how slowly, at all stresses. Of course, there can be a drop in viscosity of several decades, as the shear rate varies, and the so-called first Newtonian plateau viscosity can be very high indeed. In a series of later review articles, Barnes illustrated that, in many respects, shear stress is a more revealing variable than shear rate. So, when viscosity values are plotted in this way, as in the present graph for a 10% suspension of bentonite, dramatic changes in viscosity can often take place over a very limited range of shear stress. Here, for example, we see about an 8 order of magnitude drop in viscosity over a single decade of shear stress. Barnes went on to quote Malkin, 1994, who essentially suggested that it is reasonable to treat the behaviour of such a material at low stresses as solid-like, even though it is clearly a liquid. But it is a liquid with a very high viscosity at low stresses, so that it will flow very, very slowly. In this sense, the dramatic drop in viscosity might be considered as a transition from solid-like to liquid-like behaviour. We shall return to this and similar ideas a little later. The Barnes and Walters paper spawned a whole series of papers, expressing both support and opposition, and the debate seems to go on unabated. An early rebuttal came from Hartnett and Hu, who reported results from a falling ball viscometer. Interestingly, they based their belief in a yield stress on the fact that a specific ball did not fall a measurable distance over a timescale of 3 months. This, in turn, led to a debate on what one should define as a measurable distance, and what a reasonable time of observation should be. We shall return to this and similar issues later. In the meantime, we need to stress that Barnes and Walters were certainly not the first to question and reinterpret the yield stress hypothesis. For example, even at the first meeting of the American Society of Rheology in 1929, Marcus Reiner, one of the 3 organizers, when referring to Bingham materials, said there was no yield point. A little later, in 1933, One of the other organisers of that famous meeting, the Englishman George Scott Blair, safely hedged his bets by proposing that the yield stress was that stress below which no flow can be observed under the conditions of experimentation. Of course, some were more dismissive of the yield stress hypothesis and would have agreed wholeheartedly with the comments of Barnes and Walters. So, for example, Markowitz, Coleman and Knoll, in their influential 1966 book on rheometry, agreed that the concept of a plastic material has been greatly overworked, and almost without exception, the yield values reported have been obtained by extrapolation of limited data. When careful measurements are made below the yield stress, it is found that flow actually does take place. All this means that Barnes and Walters were certainly not the first to question the yield stress hypothesis, but their 1984 paper did seem to catch people's attention and interest, and maybe their annoyance as well. Before leaving this section, we remark that if someone were looking for a classic example of a material that appears solid-like, near the rest state, and yet on closer scrutiny is found to be a liquid, they should look no further than the ongoing experiment conducted at the University of Queensland in Australia. Interestingly, the experiment is recognised in the Guinness Book of Records as the longest-running laboratory experiment in the world. The relevant website given on the screen provides the background. The pitch drop experiment was initiated at the University of Queensland in Australia in 1927 by a physics professor, Thomas Parnell. It is now supervised by Professor John Mainstone, who is shown on the screen, standing behind the simple pitch drop apparatus. The pitch flows very slowly, drop by drop. The 8th drop, since the experiment started, fell in 2000, and the 9th drop is only just forming. The pitch is estimated to be 100 billion times more viscous than water. The fact that the pitch can appear solid-like to the uninitiated is provided by this graphic video, which is taken from the University of Queensland website and is used with their permission. We now need to bring things together and agree on those ideas and conclusions that would command general support. In this connection, the first thing we need to emphasize is that some materials that were once considered to have a yield stress have now been convincingly shown to be simply shear thinning fluids, but with a very high first Newtonian plateau in the limit of vanishingly small shear rates. Such a conclusion is beyond debate and would be acknowledged by all experimental rheologists who have access to a modern-day control stress rheometer. Having said that, there is no doubt that the concept of a yield stress is sometimes very helpful in practical situations, and in that sense, we can talk of the engineering reality of the yield stress. Indeed, the late Professor Gianni Astorita chose this as the title for a short and humorous letter to the Journal of Rheology in 1990. One of the authors of the original yield stress myth paper, Howard Barnes, is happy to agree. In his extensive 1999 review article, he states, "Without any further hesitation, we can say that the concept of a yield stress has proved, and used correctly, is still proving, very useful in a whole range of applications." In another place, Barnes affirms that much useful progress has been made in applied rheology by using simple yield stress containing equations that fit steady-state shear stress shear rate data quite well over a limited range of shear rates. And, in yet another place, Barnes is also happy to affirm that the determination of a yield stress has a rational basis when we define it as that stress below which no observable flow takes place. Of course, this leaves open the question as to what we mean by observable. And this is something else that has occupied the attention of more than one rheologist. However, to move from concepts to practical realities, we can do no better than refer to the thoughts of Bingham himself on the matter. In addressing a subject that everyone would be conversant with, he wrote, "The paint must have a yield stress value high enough so that it will not run under the influence of gravity, but the mobility must be high enough so that the painter may spread it without undue fatigue." The third thing we must mention is that there are some materials for which a yield stress arises quite naturally from respectable theoretical modelling. This can arise, for example, in the case of concentrated suspensions, where one can postulate circumstances where particles jam and are not able to move. Foam rheology is another area where essentially the same thing can occur, and we shall now describe the mathematical modelling of a two-dimensional foam using the ideas and videos of our colleague Simon Cox. Turning now to theoretical considerations, some models for idealised systems show clear evidence of a yield stress. Our colleague Simon Cox has provided us with one such example. This concerns the behaviour of a two-dimensional foam, such as can be made by squeezing a washing-up foam between two parallel glass plates. The theory is based on a single assumption, namely that the dominant energy at low strain rate is just the surface energy. In the model, the shear stress in the foam derives from the tensions in the films. There is a random distribution of bubble areas, and the films that touch the upper and lower walls are fixed to the wall, and in the case of the upper wall, move with the wall. In the model, a stress is applied to the top plate at 0 time, and the strain increased until the foam stress equals the applied stress. At a later time, corresponding to t equals 1.25 on the graphs, the applied stress is suddenly removed, and the foam left to recover. We shall show the predicted behaviour of the foam for two values of the applied stress. In the first, the stress is low. Few topological changes occur, and to all intents and purposes, the foam responds elastically, remaining stationary for most of the simulation, before returning to something close to its initial state after the stress is removed. For a higher stress, many topological changes occur. The foam never jams, and does not return to its initial state when the applied stress is removed. Here we clearly see fluid-like behaviour. Loosely, we can say that the first applied stress is below the yield stress, and the second is above that stress. So, here we have a respectable theoretical model for a material system which clearly illustrates the possibility of a yield stress, with the foam behaving like a solid below a certain stress and like a fluid above that stress. So, the story is told, and amongst all the detail that has gone before is one overriding conclusion, namely that yield stress has proved and will continue to prove a useful concept as we attempt to understand and interpret the behaviour of an important subset of complex materials.